Okay, thank you very much, and I would like to thank Gediminas for organizing this meeting. So I'm Hrvoje Buljan. I will talk about unconventional topological phases in some lattices. So the outline is here. First, I will briefly introduce a few concepts from topology, although I think most of the people here are quite well acquainted with this, just to make sure we're all on the same page. And then I will say a few things about these two papers here. This is work in photonics. What is topology? So if you would ask a person studying topology, they would tell you that all these objects that you see here are the same, they're equivalent. So the question is, what does it really mean? And to understand what it really means, we have to understand the concept of curvature. So let's consider a ball. This is like a two-dimensional manifold which is closed, and to each point on the ball we can associate the curvature, which is in this particular case is just 1 over the radius squared of the ball. If you consider a more complicated manifold, which is two-dimensional, to each point on a manifold you can associate principal planes of curvature, and then to each one of these principal planes you can associate one radius, and this radius corresponds to a circle which is just tangential to this point. And then if one of these curves is concave and the other one convex, then there would be a minus sign here in front of the curvature, and the curvature is just in magnitude 1 over the product of these two radius. So for example, if you would consider a torus, inside you would have negative curvature and outside positive, and in magnitude just 1 over product of these two radius. So in fact, what is topology? In this particular case of surfaces embedded in three-dimensional Euclidean space is the Gauss-Bonnet theorem. If you integrate the curvature over this closed surface, you will get 2 pi times an integer. So for a ball, it would be 2. For torus, it would be 0. For this pretzel type structure, it would be -2, and so on. So in fact, this number here we would call a topological invariant, and this is a characteristic for one of these surfaces. So as long as you don't break the surface or you introduce another hole, this number will stay the same. You can change it, you can smoothly deform it, but if you don't break it, if you don't introduce any other holes, this number will be the same. And then in physics, I think the most important connection between physics and topology is a quantum Hall effect that was actually already mentioned today in the morning. And what is the connection? Well, in the quantum Hall effect, you have current going through a system of two-dimensional electrons in a uniform magnetic field, and you can measure voltage. And then when you have voltage and the current, you can also define resistivity or conductivity. If you calculate this conductivity for this system, by using the standard Kubo formula from condensed matter physics, what you find out is that it is related to this charge of the electron squared divided by the Planck's constant times c. And c here is actually the Chern number. It is the topological invariant associated to this system, integral of the Berry curvature of over the Brillouin zone, and these guys here were the first ones to actually discover that. And this actually gives rise to very robust measurements of the conductivity on these plateaus. The experimental error is like 10 to the minus 12. And now these concepts were translated to photonics, and the first one that was studying this theoretically was Haldane and Raghu, and then Marin Soljačić in his group did the first experiment studying topological edge states, because to each of these Chern insulator condensed matter systems, there are these topologically protected edge states, and he was measuring them in the microwave domain in optics, and then in the optical domain there were several experiments later on and some really nice reviews that you can find on this topic. And of course these concepts were translated to ultra-cold atoms in the groups of Ketterle, Immanuel Bloch, Esslinger, and also in mechanical systems you can find this. I think all of you are quite well aware of these things. And after this brief introduction, I would like to start saying a few things about the first paper that I will talk about. These are subsymmetry protected topological states in some photonic lattices that we studied. So first I want to introduce what is a symmetry protected topological phase. Symmetry protected topological phase, first let's start with topological insulators. So as I have already explained a little bit, if you have a topological system which is described by a topological invariant, if you change it a little bit without breaking it, without changing this topological invariant, it will be quite robust. And actually topological insulators are also robust. However, there is a little caveat with these symmetry protected topological phases. You can perturb it, but this perturbation has to conserve a certain symmetry. If it if the perturbation respects a certain symmetry, in this particular case, time reversal symmetry, then topology will be preserved and you will have robust, let's say, topological boundary states. And there are topological crystalline insulators where certain crystalline symmetries have to be preserved when you perturb the system to retain your topology. And perhaps the simplest system that you can have, which is a symmetry protected topological phase, is the SSH lattice. So SSH lattice is very simple. It has only two sublattices, A and B, and there is nearest neighbor hopping between these sublattices described by the two parameters, T1 and T2, and here is the Hamiltonian. So when T1 is greater than T2, then this system is in a topologically trivial phase, and you can characterize it by the Zach phase. This is the topological invariant in this system. And when it's in a topologically non-trivial phase, this topological invariant W, the winding number, is 1. And the physical manifestation of non-trivial topology here are the edge states that you can find when your system has a finite size. So these two things, topological invariant and edge states, are characterizing the non-trivial topology in this simplest symmetry protected topological phase. And the symmetry that is behind this is the chiral symmetry. So you can define a chiral symmetry operator, which is just a projection operator on the A sublattice minus projection operator on the B sublattice. And chiral symmetry is described with this equation. So as long as you perturb this system by a perturbation which respects this symmetry, your topological invariant will be preserved and also the edge states will be preserved. And the question that we were wondering is whether you can perturb this system and destroy the topological invariant, but still somehow preserve the boundary states. And of course also whether you can destroy the boundary states and preserve the topological invariant. What we were wondering whether we can classify these perturbations by using symmetries. And in fact, you can do this by using this concept of subsymmetry. So what is this concept of subsymmetry? It's actually very simple. So when you have a symmetry, you describe it by a certain operator equation, which is valid in the entire Hilbert space of your system. So for this particular system, you can define subsymmetry by attaching this projection operator PA on the right-hand side of this equation. So this would be A subsymmetry, this would be B subsymmetry. So what does it actually mean? It means that the symmetry equation does not hold in the entire Hilbert space, but only in part of the Hilbert space, here only on the A sublattice, and here only on the B sublattice. So Actually, very simple concept. And then in this particular system, what does it mean? So this here, the black circles here, they represent the energy diagram of the SSH model in the non-trivial regime. So what you have is two bands, because you have two atoms in a unit cell, and you have these two edge states which are exactly at zero energy because of the chiral symmetry in this system. So what happens when you perturb the system by a perturbation which respects, let's say, this A subsymmetry? What happens is that the mode which is on the A sublattice, so each of these topologically protected edge modes are also eigenstates of the lattice on the sublattices. They're either entirely on the A sublattice or entirely on the B sublattice. So this one is on the left, on the A sublattice, and it is entirely protected by this subsymmetry, whereas the other one on the right-hand side, it is pushed down towards the band, and it loses the characteristic features of the topologically protected edge state. So this is an example where you destroy the topological invariant, you destroy one of the edge states, but the other one stays intact because of this subsymmetry. And then the previous slide was for just one randomly chosen perturbation. So this is for many 70 randomly chosen perturbations, and then we plotted energy for different perturbation strength for all of these, one on top of each other. So you can see that the red circle, which is the mode on the left, is protected by this A subsymmetry because it resides on the A sublattice, whereas the one on the right is changed and eventually merges with the bulk when you increase the strength of the perturbation. So this is for the BB coupling, this is for the AB and BB coupling. All of these preserve this A subsymmetry and destroy the topological invariant and the mode on the right-hand side. And then these are also simulations where we studied the projection of the operated of the state that is not preserved, this topologically protected state, and the one which is preserved. And also we inserted PA operator here, which tells us whether there is some leakage from the A sublattice to the B sublattice, which would indicate that maybe this is no longer protected. So you see the blue cross is here, it's exactly one, and here the finite size effects start kicking in, and you can see a little bit of deviation from one, which tells us that indeed this thing works quite well for quite strong perturbation strengths. And now I want to show experiments. So these experiments are done in photonics, in laser-written waveguides, where you can actually, so maybe this slide describes the system better. So X and Y in this system is space, and Z in this system is time. And what you have is a photonic structure which has some corrugation along the X or Y, and it is constant along Z. And from this side, you insert laser light, and it propagates. You can describe it by a Schrödinger equation in 1 or 2 dimensions. So this is the same as quantum physics in 1 or 2 dimensions, but without interactions, only single particle physics. And so this is an experiment showing what happens when you perturb your system by A subsymmetry preserving perturbation. This is BB coupling and only local perturbation here. And this is A subsymmetry breaking perturbation. And the laser light initially excites the mode on the left, which is here protected. As you can see, it doesn't couple at all onto the B sublattices, whereas here, where it is not protected, it couples to the B sublattice, and it is no longer a topologically protected state. So these are the simulations. So this is for a local perturbation, but we also did experiments, actually not me, my collaborators did experiments by using perturbations which are periodic. So by using this zigzag type structure in optics, you can write this waveguide spatially at will. You can introduce BB or AA coupling, and then have these periodic A sub C breaking or A sub C preserving perturbations, and the experiments agree with the theory about protecting of these modes. So this was for the simplest case, and I'm not going to show results for the Kagome lattice, but in the Kagome lattice you have this generalized chiral symmetry, and you can define 3 different subsymmetries for a Kagome lattice. And in optics, the nice thing you can do these couplings and quite judiciously introduce couplings between different sites and test the theory in experiments. So here you see these little peaks here mean that a subsymmetry is broken and the topological edge state is no longer protected. And now I will move on, and please let me know if I'm out of time. Just a few more slides. The title of the talk is Unconventional Topological Phases. So this is one unconventional topological phase where we were studying lattices which have some restrictions on the coupling. So in a unit cell, we have n plus j unit sites. So this means n plus j unit lattices. And some of these sites have restricted coupling along some of the dimensions. For example, here is an illustration of a 2-dimensional lattice, and there are 3 atoms in a unit cell, and these 2 don't couple along a vertical direction. They do couple along the horizontal direction, and for the 3rd one there is no restriction at all. So there are quite a few lattices which have this type of structures. And when you calculate in a tight binding regime how does this lattice look like in K-space, the matrix looks like this. So there is a Hamiltonian, a block diagonal here, which is n by n, which corresponds to the coupling inside the unit cell. And then there are ones in a there is a J by J matrix here, and then the coupling between the 2 sectors. So when you have this type of lattice, what you can do is you can start from the original Hamiltonian that I have shown, and by using a well-defined procedure, you can define auxiliary Hamiltonians. And to each of these auxiliary Hamiltonians, in a very simple way, you can define topological invariants. They are just winding numbers here. And there are boundary states which correspond to these auxiliary Hamiltonians, but you can also show that they are exactly correspond to the boundary states of the Hamiltonian system. So these boundary states will be protected because of these topological invariants here. And what we found out is that even if the original system is by conventional knowledge not topological, that actually these boundary states will be protected by the topological invariants arising from these auxiliary Hamiltonians. And we have applied this simple theory not only to 1D topological insulators like SSH or 2D higher order topological insulators, but even for some Chern insulators where you have a well-defined topology in terms of the Chern number, this theory seems to predict better where you can find the boundary states. So let me try to explain it once more. So you start from this original Hamiltonian, you apply the symmetry transformation, and then you have diagonal Hamiltonian here. And then this is an n by j block. If you just take one row from this block, you can define such an auxiliary Hamiltonian. Well, this is exactly the SSH type Hamiltonian and the SSH type topology. It has chiral symmetry. You can easily define the winding number, and then you have boundary states associated to this auxiliary Hamiltonian, which exactly correspond to the boundary states of the original one. So here's the simplest example that we had of a quasi one-dimensional lattice where you have 3 atoms here, A, B, and C in the unit cell. By using this procedure, you can find that there are 2 auxiliary Hamiltonians here, and each of the 2 Hamiltonians are exactly the same as the SSH model, and then you can find the boundary states and so on. So when you calculate the winding numbers for this exactly the same system, you can find out that the winding numbers exactly predict where do you have boundary states in this system. So this is a plot of the energy structure. As you change parameter T is one of the couplings there. All the other ones are held fixed. And the winding numbers correctly predict the location of the possible edge states that you have here. And then this was also done by my collaborators in the experiment. What they did is they created these lattices and arranged the coupling so that here you have both topological invariants, here you have only one, and here you have zero. So I'm not going to show the details. You have two boundary states here, only one here, the other one is not stable, and zero boundary states here. And also as I have said, for one particular churn insulator, we have calculated the boundaries. So this one, I have to say, has indirect gap. This is an important feature here. The gap is not direct, but it's indirect. Still, you can calculate the churn numbers. For one band is 1, for the other one is -1. And depending on the parameters, sometimes you will not have boundary states at all. So our theory correctly predicts not only whether you have or you don't have the boundary states, but it also correctly predicts where they are located in K-space. So this is for a strip of this material calculation. From the churn numbers, you would say that you should always have boundary states, but this is not really true. And this brings me to the end of my talk, and I'd like to thank my collaborators for working on this, and I'd like to thank you for listening to me.
One question that is bothering me a lot, I mean, the two papers that you presented, are they unrelated or two faces of the same thing? They don't really know.
No, they are somewhat related. So the question is for the first paper, and I must admit I don't know entirely the answer. For the first paper, you could ask me, for example, okay, the topological invariant, that is the standard one, the Zach phase is no longer okay. Is there another one, right? So with the second paper, we were trying to find out whether there is another one that could be associated to these edge states which are still protected, but honestly, I don't know the answer right now. So, yeah.
When you say indirect gap, what do you mean and why is it significant here?
Okay, so this is actually a really important thing. So indirect gap means that you have energy as a function of K. Mm-hmm. If I project it onto a single line, I will not see a gap. But I can put my hand through, so bands never touch. Yeah, but it goes like this, okay? Sure. So if I project it, I will not see a gap in a projection.
So, but that's different from an indirect gap in, say, a semiconductor, where the maximum and the minimum can be at different points, but there's still a real energy gap between.
You're right, yeah. Okay. Maybe I should have be more cautious in explaining this, yeah.
Thanks.
Yeah, very nice talk, thank you. If I understood correctly, your notion of topology mainly concerns the edge modes, like you would say something topological if it has an edge mode. But could you learn also something about the bulk response via your formalism, if you had a bulk system in 2D, for example?
So topological invariant is related to the bulk. Okay. So of course, the question is whether these topological phases belong in one of these in the classification, right? But the last one does not. So we cannot classify it. So maybe somebody would say that this is not even topological at all. I mean, but this is name, okay? So what happens here is that you can define these auxiliary Hamiltonians. They have the SSH type structure, and you have boundary states which are exactly like the SSH type boundary states. Yeah. That.
Yes.
Oh, okay.
It's bad. You need to Thank you, Hrvoje. So you said in the last part that you need to have a rotation that puts subparts of your Hamiltonian into, block diagonal form of some sort that then allows you to then identify SSH subparts, right? So I mean, we had a similar thing when we squared once the Hamiltonian, and then it also reformulated itself into something like this, and then we could also understand subparts of this. How do I know? And then after doing that, we saw that actually this squaring procedure ended up looking like some sort of non-symmetric spatial symmetry. So it's all interrelated in some sense. How do you know which rotation you have to do in order to identify which?
Okay, I think here it's actually very simple. So in the unit cell, you have, let's say, some certain number of atoms, right? And then your eigenmodes have a complex, they have an amplitude and phase at each one of these sites. So this initial diagonalization of one of the blocks simply means to uncouple things within the unit cell. So I think it's much simpler than what you are mentioning with respect to squaring and all these things that maybe that's more complicated. So this is, I think, very simple. It's not, no mystery behind.
Thank you. And I have a very strong suspicion Gediminas wants to announce something, right? Yes. So please do.